this session we are going to study a little more the chemical affinity. Using equation 26 of the previous slides for the chemical potential as some function zeta of the pressure and the temperature plus another function of the molar fraction big N gamma, and also using equation 28 for the affinity, which is equal to minus the sum over all the components in the system of the stoichiometric coefficient for the component times the chemical potential of the component, we can arrive at this equation 40 for the affinity. We now introduce a new variable which will be called the equilibrium constant, K, which is a function of pressure and the temperature. And we introduce it by setting RT times the logarithm of K equal to the first term in equation 40 for the affinity. So equation 41 is just the definition of the equilibrium constant K. Therefore, using the definition, equation 41, in equation 40, we can then write the affinity in this form, which is the affinity is equal to RT, that is the gas constant times the temperature, times the logarithm of K, minus RT times the sum over the stoichiometric coefficients times the logarithm of the molar fraction. Therefore, the affinity takes on this simple form, just RT times the logarithm of the equilibrium constant over the molar fractions raised to their stoichiometric coefficients, each one of them being multiplied by the others. Now we know that in equilibrium the affinity is equal to 0, and the only way equation 42 can go to 0 is if the function, the log, goes to 0, and that is only the case when the fraction K over the molar fractions multiplying each other goes to the value of 1, because the log of 1 is equal to 0. And therefore that implies that the equilibrium constant K then is just equal to the multiplication of all of the molar fractions raised to their stoichiometric coefficients. And this equation, equation 43, is called the law of mass action. So equation 43 is only valid when the system is in equilibrium, when the affinity is equal to 0. So that is why K is called the equilibrium constant. Now we can also write an alternative form for the affinity by using equation 1 for the chemical potential in terms of the Gibbs free energy G. And so if you look at equation 21, you will see that we can then write the affinity as being equal to minus the sum over all the components in the system of their stoichiometric coefficients times partial G by partial N, the number of moles of substance gamma, at constant pressure, temperature, and all other mole numbers. So all other mole numbers are kept constant while we do the partial differentiation of G with respect to the component that we are looking at. By realizing that the advancement of the reaction G depends on the mole numbers N, we can write partial G by partial G at constant pressure and temperature is just equal to the sum over all the components in the system times partial G over partial N gamma at constant pressure, temperature, and all other mole numbers times dN gamma by dG. That is just an expansion of N in terms of G. But going back to the previous lectures, we know that dN gamma by dG is just equal to the stoichiometric coefficient, nu gamma. So we have then the last term of equation 45. Therefore, comparing equation 45 with 44, we can write the affinity as just being equal to minus the partial of the Gibbs free energy with respect to Chi at constant pressure and temperature, which is equation 46. Now, remembering that the Gibbs free energy is just the enthalpy minus the temperature times the entropy, we can write equation 46 in the form of equation 47. Now, minus the partial of the enthalpy with respect to the advancement of the reaction Chi at constant pressure and temperature is called the heat of the reaction, and we signify that by this R. This is R at constant pressure and temperature, which is known as the heat of the reaction. So R is actually the heat which is given off by the reaction. If it's exothermic, it will be positive. If it's endothermic, it would be negative. The last term of equation 47 represents how the entropy of the system is changing with respect to the advancement of the reaction at constant pressure and temperature. Now, in some cases, it may be possible to neglect the entropy variation term, that is the last term in the previous equation 47, so that the entropy production, due to a chemical change or chemical reaction, then becomes simply proportional to the heat of the reaction. So if we neglect the last term in equation 47, we can write the entropy production as just being equal to the affinity times the rate of the reaction over the temperature, and that is approximately then equal to the heat of the reaction times the rate of the reaction over the temperature, or minus 1 over T times dQE by dt, where T, the small t, is the time variable at constant pressure and temperature. So this dEQ is just the heat given off by the reaction, and it goes to the environment, or it comes in from the environment if the reaction is endothermic. So therefore, equation 48 is telling us that if we want to calculate the entropy production of a system, often, but not always, we can determine it only from the heat of the reaction, the heat which is being produced or flowing from the system, whether it be positive or negative. But this is only the case when we can neglect the variation of the entropy, how the entropy is changing within the system while the chemical reactions are occurring. So I would like you to consider under what conditions can the entropy production term be neglected. And I'll just give you a hint. For example, when humans reach the age of about 30, their physical appearance doesn't change. They increase their weight a little bit, but ignoring those who are getting fatter, the physical appearance of an individual is not changing. Therefore, the entropy of that individual should not be changing, and we can determine the entropy production of the individual by the heat which is being given off by the individual to the environment. That is an example. So the case we have given is just for one chemical reaction, but we can do the same for a system in which there are multiple simultaneous chemical reactions occurring. Then to determine the entropy production, it is just approximately equal to the sum over all the heat of reactions times their rates, the velocity of the reactions. So we just do a sum over rho, where rho is the indice which indicates which reaction we're taking into account. and that is equal to the total heat which is being given off to the environment or taken in from the environment in the case of endothermic reactions. So in this approximation in which we can neglect the change in the entropy of the system while the reactions are occurring, the entropy production of this system, or a living system or any system, can then be measured by its metabolism as recorded by calorimetry. Now let's consider the case that we have an open system and we study the entropy production due to the flow of matter and heat from the external environment and allowing chemical reactions to be occurring within the system. So therefore the Gibbs equation for this system is just ds, the change in entropy, is equal to d phi over t. Remember, phi is the energy which is being brought in to the system or given out to the environment. It composes both the heat and the energy which is on the material, because now this is an open system, so material is coming into the system or leaving the system, and this material can carry energy itself. So we have to include both the flow of heat and the flow of energy, and that's why we write d phi instead of dq. Always in open systems we will find a d phi rather than a dq. Okay, so that's the first term. The second term is minus the chemical potential over the temperature times dN gamma. Now this dN gamma represents the material, the number of moles of substance gamma being brought in or given out to the environment. And that's why we have a subindice E, which signifies external environment. So that is the flow of matter, the second term. And the third term are the chemical reactions, just the affinities times dG over the temperature. So the force in this case is the affinity over the temperature, and the flow is the rate of the reaction, or just dG by dt, where t in this case is the time variable. That's equation 50. Therefore, the first two terms of equation 50 represent the change in entropy of the system due to the flows from the external environment, the flows of heat and energy, plus the flow of material. So we can represent that as DES, which is equation 51, which just comprises the first two terms of equation 50. Now let's consider a system consisting of two open subsystems, but which is closed as a whole to the environment. So between the two subsystems there can be a flow of energy and a flow of matter. But to the environment there can only be a flow of energy. So for this system, the Gibbs equation, equation 50, becomes this equation 52, where we have now the two subsystems that we have to label 1 and 2. So the first two terms are the flows of energy into the respective subsystems 1 and 2. It can be from the environment or from the other subsystem. And the second term represents the flow of matter. Now the flow of matter we are not allowing from the environment because we are saying that the system as a whole is closed. So we only allow the flow of matter from subsystem 1 into subsystem 2 and vice versa. And the last two terms are the chemical reactions which are occurring in subsystem 1 and subsystem 2. So these are internal to the system. Now you might ask, why is there a minus sign in the parentheses of the second term? Well, that is just due to the fact that we're only allowing matter to flow within the system from 1 to 2 or 2 to 1. And the flow from 1 to 2, of course, is going to be the negative of the flow from 2 to 1. So that's why we are just using DEN1 gamma and putting a minus sign. because the flows are equal, have to be equal and opposite. Now, since the system as a whole is closed, we can only have heat being coming in over the boundary. We cannot have mass being come into the system over the boundary of the whole system. So therefore, we can, the first two terms of equation 52, we can write as these first three terms of equation 53. So the subindice E represents from the external environment. So from the external environment, only heat can flow. That's why it's dQE for subsystem 1 and subsystem 2. But internally, between the two subsystems, we can also have a flow of matter, and this matter can also be bringing in energy. That's why we use d phi. And of course, the flow of the energy being brought in by the mass from subsystem 2 to subsystem 1 is the negative from 1 to 2, and that's why, again in the parentheses, we have a minus sign. And the final two terms are just the final two terms of equation 52. Again, they represent the flow of matter from 1 to 2 or 2 to 1, and the chemical reactions which are occurring in system 1 and system 2.